Okay, so let us start with week 5 of problem solving session for the course of Introduction to Fluid Mechanics. I hope I am properly audible. So, first of all, we'll go through what was being taught in today's session, like today's course. This course, like in the classes, what sir have taught you already. So, sir have covered the class for the fluid kinematics. So, basically, let us first discuss what fluid kinematics is. So, to understand the particle mechanics or to track a particle motion, whether that may be considering individual particles, or that may be considering the a position as a whole. So whether the approach may be, whatever the approach may be, the phenomena for tracking the particle motion is called fluid kinematics. So if we go for further explanation, there are two approach that are being considered till now for tracking the fluid particles. That is, first one is Lagrangian approach, and another is Eulerian approach. So if you are tracking a particle motion, then uh, individual particles, like if you are tracking the velocity of the individual particle or the properties of individual particle like acceleration or others, that approach is called Lagrangian approach. And if we do not track a particle, rather we give value to the position and track a position, that is called Eulerian approach. So let's suppose, if I'll explain you further, let's suppose these are three axes, x, y, and z axis. And we are considering a particle here that is at a distance r naught, that is at a distance r naught from the origin. So this particle, if we are tracking, like let's suppose this is following a path like this, right? So we are tracking this particle as a whole, like which path it is following at what time. So this is Lagrangian approach. But let's suppose we are, sorry, let's suppose we are considering another position r, and we are fixing this position. That means whatever particle may pass through it, we are not tracking particle. We are fixed on the position itself. And whatever particle is passing, we are just taking the characteristics of or the properties of that particle. Sorry, particle that is passing through this position rather. Okay, so this approach is called Eulerian approach. Okay, so I hope that's clear. So the terminologies that sir have undergone or sir have taught in this previous classes are, let us go through those terminologies first. Okay. So first one is steady or unsteady flow. So what is steady and unsteady flow? If the fluid properties changes with time, that is called uh, unsteady flow, and if the fluid properties are not changing with time, that is called steady flow. Okay. So if let's suppose there is a pipe, this is the pipe, and the fluid is flowing through the pipe. Let's suppose we are considering velocity here. So let's suppose this is the velocity in this direction at time t1, and at time t2 the velocity are changing, right? Here, like that. So that means at each point of time the velocity is changing. So this is unsteady flow, and if it remains same, that is steady flow. Next is uniform or non-uniform flow. What is uniform non-uniform flow? Let's suppose this is the pipe or the cavity through which the fluid is flowing. If this is the direction of the velocity vector, every time this is pointing towards the same direction. Let's suppose this is point x1, position x1, sorry, x0, and this position x1. At position x1, these are changing. That means at both of the positions, the velocity vectors direction are different. That means it is changing with position. That means it is non-uniform flow. And if it is fixed, like let's suppose it has changed at x1 to this. Tell me what kind of flow is this? This at time t1. This is at t0. This means the directions have changed. The direction of the velocity vector have changed, but still it is uniform. Like with position, it's not changing, right? At every position, it's same. That means the flow is uniform, and but still it is unsteady. Okay. Now let's suppose now let us point what is steady and non-uniform flow. Like if we want to draw this up. So if this is the case, let's suppose at point x1 and at point x2, at a time t1 and at a time t2, these are similar, but the direction of velocity are changing. Like all total direction are same, but at time from x1 and x2 it is different. Like in position x1 and x2, the velocities are different, the direction of velocity is different, but at time t1, between time t1 and t2, they are same. Like if I consider one fixed position, the velocity vector in that position is changing. Like sorry, with time it's similar. That means if I am considering time like at 0, and if I am considering 5 minutes later, the velocity vector at this position will be same, in the same direction, but with position it is changing. So this is non-uniform and steady flow. Now let us understand what is the choice of frame of reference. Basically, whether a flow is steady, unsteady, or uniform, non-uniform, that is depending upon the frame of reference. That is, whether a frame of reference is fixed or the frame of reference is moving with a constant velocity, that will determine that a flow is steady or unsteady. Like the point of observation of a person actually. Let's suppose a person is standing at the bank of the river and another person is on the boat traveling in the river. The person in the bank will see the person in the boat moving from point A to point B, and the fluid velocity changes along with it. So the person will think that the flow is unsteady as the flow, what is happening, the flow is changing with time, because it is like at some fixed position, there was one kind of flow and it is changing as the boat is moving from here to there, right? But for the second person who is moving on the boat, with for him the boat is also moving and the water is also moving in the same velocity, right? Because the boat is moving in the water itself, so the relative velocity is zero. Thus he will feel that the boat is like the velocity of the fluid is stationary. So it depends upon the frame of reference, what is the velocity of a flow, right? So one frame of reference can be transformed into another. Such transformation is called Galilean transformation. Okay. So now let us consider some basic terminologies. Those are streamlines, streak lines, and path lines. First, let us consider what is streamline. This is an imaginary line that is the tangent to which will give the velocity vector at that point at that instant of time. That means, let me consider some other color. Like this is the streamline, right? If I consider at this point, this is the velocity vector. If I consider at this point, this is the velocity vector. If I consider this point, this is the velocity vector. So at any point, it will give the velocity, the tangent to which will give the velocity vector, that is called streamline. Let us suppose, let me take some other color. Let us suppose, let us take a point from here to here, P1 and P2, whose thickness is dr, dr vector. So the let's say that this this dr and this v vector are parallel to each other. This will happen if P1 and P2 are very close to each other, right? That means, just one second. Okay, so that means this is so small, this dr vector, sorry, this dr vector is so small that dr vector can be considered parallel to b vector, right? Then this dr vector is also acting like tangent to the streamline at p1. So if we write cross vector of dr to b vector, that can be written as ijk dx dy dz, because dr vector is dx I cap, dy j cap, and dz k cap, and v vector is u I cap, v j cap, and w k cap, right? So we can write here u v w. So this is equal to 0 vector. So if we will break down the determinant, this will be w dy minus v dz is equal to 0. W dx minus u dz is equal to 0, and v dx minus u dy is equal to 0. So this can be written as dx upon u, dy upon v, dz upon w. This can be considered as equation for streamline. Now we will understand what is the streak line. But before understanding streak line, let us first understand what is path line. So path line is the locus of an identified fluid particle. That is the path that the fluid particle has followed. Is called the path line. Let's suppose there is a point 1, right? And let's suppose the fluid particle has traversed this path. Then there comes another particle which has traversed this path. Then there came another particle that passed through point 1 which has traversed this path. So if we join this final position of all the particles that at some point of time t has passed through this point, this position 1, then this line that has formed, this is called streak line. That means this is path line 1, this is path line 2, this is path line 3, right? And this is t is equal to t3, this is t is equal to t1, and this is t is equal to t2. That means this has crossed this point position 1 at time t1, like the first particle, second particle has crossed at time t2, and third particle has crossed at time t3. And now at any time t, the line that is the locus of all the points connecting the initial position and the final position of all the particles, like at any time t, obviously there will be particle at position 1. So if you connect all the lines or locus of all the points of all those particles that is passed through that point, that is called streak line. Okay, so you have understood path line and streak line. Now for steady flow, there is one important observation, that is for steady flow, streamline, streak line, and path line are identical. Okay, now let us consider a simple problem, like if we consider a 2D velocity field. Let's suppose u is equal to ax 1 plus 2t, v is equal to by, and w is equal to 0. So we have to find the equation of streamline streak line at t is equal to t1 and find the equation of path line. Streamline is very easy, like dx upon u, dv upon v. So first I'll give you some time, like at t equal to t1 you need to find out the equation. I'll give you some time to do that so that you can understand this concept by yourself. I'll wait for that time. Okay, let's try and solve this then. This will be dx upon ax 1 plus 2t is equal to dy upon by, right? So if we take a time at t is equal to t1, this will be dx upon ax 1 plus 2t1 is equal to dy upon by. So this will be 1 upon a 1 plus 2t1 ln x is equal to 1 by b ln y plus c. This is the equation for streamline. Now we have to find the equation for path line. So equation for path line will be in terms of x and y, right? So if u is given as ax1 plus 2t, so dx, the equation will be in terms of x and y, so dx upon dt, and in path line the t is a variable, like the particle is passing and we are tracking a particle, so we don't know the time, at what time like we need to track, right? So we will track the particles, so the positions we know, that is initial position and final position, x naught, y naught, next y, right? So we need to replace t. So how to do that? Dx dt, u means dx dt, that is ax 1 plus 2t. That means x naught x 1 upon x dx is equal to t naught t a 1 plus 2t dt. So if we will integrate it, ln x upon x naught is equal to a t minus t naught plus t square minus t naught square. V is equal to by. dy dt is equal to by. That means y naught to y, dy upon y is equal to b 0 to t dt. If we will integrate it, this will be ln y by y naught is equal to bt minus t naught. Eliminate t to write y as a function of x, and t is a variable. So in path line, T naught is fixed, T is not fixed. Initial time is fixed. So, what we need to do, there are two equations, right? This and this. We will just eliminate T from this both of the equation and write Y in terms of X. Okay. So, for streak line, we look at the locus of all the particles at some instant of time. All the fluid particles passing through a common point. Like if this is a point, if this is a point x naught, y naught at time t naught, and this moves to a final time tf, this is the dye when dye is injected, and this is when dye injection end. So if we take a time in between both of them, that means let's suppose t initial at some time ti between the t naught and tf, when this strict line will be found. So t naught is fixed, tf is also fixed, but ti is not fixed, so we need to replace ti at the end. So now ti need to be eliminated. So similar way we will do as we have done earlier, the derivation. So dx upon dt is equal to ax 1 plus 2t, x naught to x, and 1 upon x dx is equal to tit a 1 plus 2t dt. Then ln x by x naught is equal to a t minus ti plus t square minus ti square. For y, dy by dt is equal to by. If we will integrate it, this will be y naught to y 1 upon y dy is equal to ti to t b dt. So this will be what? Ln y by y naught bt minus di. This is equation 2. This is equation 1. Now we need to do what? We need to eliminate ti using 1 and 2. Similarly, previously we eliminated t, now we will eliminate t. Write y as a function of x because here ti is arbitrary. So we are eliminating ti. The equation that we will be getting at final, that is the that will be in terms of t naught tf and y naught x naught. So that will be the final equation. Okay. Now what is timeline? Timeline is a snapshot at different times that gives the evolution of the flow. Now next thing that we'll learn is acceleration of fluid flow. Like I have two positions, P1 and P2, right? So if I have two positions P1 and P2, let's suppose P1 is a position that has V1 is equal to R1T, that is equivalent to U X Y Z T V X Y Z T and W X Y Z T. Okay. Now another point P2, that is V2 R2T, that is equivalent to U plus del U, X plus del X, Y plus del Y, Z plus del Z, and t plus del t. Similarly, v plus del v, similarly w plus del w. Okay, so if we find the x component of velocity, that will be u plus del u is equal to u plus del u del t plus del u del x plus del u del y plus del u del z plus higher order terms. So this will get cancelled out. Which one? This one will get cancelled out. And we'll divide both sides by delta t. So it will be delta u by delta t is equal to del u by del t plus del u by del x del t plus del u by del y del t plus del u by del z del t. Now, if you find acceleration along x-axis, that will be limit del t tends to 0, del u del t. So, del u del t plus limit del t tends to 0, del x upon del t, del u del x. Similarly, limit del t tends to 0, del y del t, del u by del y. Similarly, limit del t tends to 0, del z del t, del u by del z. And let me use some other color. This is u, this is v, this is w. So if I'll write everything down again, like in simple terms, this will be is equal to ax will be is equal to del u del t plus u del x plus v del u del y plus w del u del z is equal to substantial derivative of u. And this is the temporal term, this is the convective term, component rather. So d dt is equal to del t plus u del x plus v del y plus w del z. Okay. Now this part is we can write as v del, okay, where del is I del x, I cap del x, j cap del y plus k cap del z. And v can be written as ui plus vj plus w. Okay. Next thing that we'll learn is deformation of fluid elements. So deformation is linear or it can be angular. Linear means change in volume. So let's suppose first we'll consider linear deformation. So for linear deformation, let us consider a fluid volume first. Let's suppose this is the fluid volume. Del z, del y, del x, y, x, z. Okay. So this is, if this is the boundary, this is u del t, and this is u plus the change due to this position movement, del u del x, del x, del t. Like fluid is displaced up to this, from here to here, right? So the change in length along x is del u del x, del x del t. Then change in length along y is del v del y, del y del t. Now for x, elemental strain along x is equal to del u del x del t. Cause elemental strain means this change divided by del y. Now we will find rate of strain. So this means elemental strain upon time. So rate of strain along x is equal to del u del x. This will be denoted as epsilon x. Similarly, epsilon y is equal to del v del y. Epsilon z is equal to del w del z. Rate of change in volume. So what is the rate of change in volume? If you want to find out the volumetric strain. So the old volume is del x, del y, del z, right? So after some time delta t, we will have a new volume. So what is the new volume? Let us find the change in length first. New length along x, that is del x plus del u del x del x del t. So that is del x 1 plus del u del x del t. Similarly, new length along y will be is equal to del y 1 plus del v del y del t. Similarly, new length along z is equal to del z 1 plus del w del z del t. So the new volume all total is equal to new volume is equal to del x del y del z multiplied by 1 by del u del x del t, 1 plus del v del y del t, and 1 plus del w del z del t. So now change in volume is new minus old. So that is equal to del x del y del z 1 plus del u del x del t, 1 plus del v del y del t, 1 plus del w del z del t, minus del x del y del z. Okay. So this will be is equal to, if we'll take del x del y del z common, del x del y del z will be common. This will be 1 plus del u del x del t, 1 plus del v del y del t, 1 plus del w del z del t, minus 1. So this will be is equal to, this is initial volume. So if we'll multiply all of this, and then we can write as del x del y del z multiplied by del u del x plus del v del y plus del w del z delta t plus higher order terms. So higher order terms will neglect. So now rate of volumetric strain, rate of volumetric strain is equal to new volume minus old volume upon old volume multiplied by delta T. So this will come out to be del X, del Y, just 1 second. Del U del X plus del V del Y plus del W del Z. So 1 upon V, see this volumetric strain means 1 upon V, substantial derivative of V. Del U del X plus del V del Y plus del W del Z. So this is equal to del of V. Okay. Now last thing that we will do, like, see, first let us understand this. For incompressible flow, this will be 0. That means the rate of volumetric strain is 0, because for incompressible flow, obviously there is no change in volume, right? So next, for continuity equation. So for continuity equation, let's suppose I have a fluid element of mass m. Now m is equal to rho of V. Now take ln on both sides. So ln m is equal to ln rho plus ln V. Now if you differentiate with respect to t, 1 upon m dm dt is equal to 1 upon rho d rho dt plus 1 upon v dv dt. So this is 0 because there is conservation of mass. So this is 0 is equal to 1 upon rho d rho dt plus 1 upon v dv dt. So this is 1 upon rho d rho dt is equal to plus del of v. So this del of v can be represented as del u del x plus del v del y plus del w del z. So this is written as 1 upon rho del t plus u del rho del x plus v del rho del y plus w del rho del t plus del u del x plus del v del y plus del w del z. This thing. Now this can be written as del rho del t. This rho will be going on this side. Here it is 0, right? So del rho del t plus u del rho del x plus v del rho del y plus w del rho del z, right? Plus rho del u del x plus rho del v del y plus rho del w del z is equal to 0. Now, if we consider these two terms, can't this be written as like this? Del x of rho u? Obviously, it can be written as that. So, if we write the whole of the equation in this form, del rho del t plus del x of rho u plus del y rho v plus del z of rho W is equal to 0, right? Now, this can be written as del rho del T plus del of rho V is equal to 0. This is the final equation. This explains the law of conservation of mass, that means the continuity equation. One important thing to note here is velocity field should always satisfy continuity equation because of conservation of mass, right? So any velocity field should follow the conservation of mass, obviously. So that means if velocity field is given and if it is asked us that whether this velocity field exists or not, then we'll just use this equation to identify whether this equation is followed or not. If it is followed, then obviously that velocity field exists. So for special cases, for steady flow, obviously for steady flow this will be 0, so only this will be existing, like del rho of V is equal to 0 for steady flow. And for incompressible flow, del del x plus del del y, like for incompressible flow, like this del rho del x, y and z will be 0, del del t will also be 0. So only del u del x plus del v del y and del w del z we can write as 0. Right. So this is all for the recap of what happened in the whole week, what's taught. Now we'll proceed to today's questions. So this is the first question for today. A flow is said to be uniform when? Obviously, the flow velocities and fluid properties do not change from point to point position in the flow field, right? So flow velocities and fluid properties do not change with time at any point. Sorry, just one second. If flow is said to be uniform when the flow velocity and fluid properties do not change from point to point, that means the position does not change in the flow field, then it will be uniform. And if it does not change with time at any point in the flow field, that means it is steady. Okay, so we're done with first question. What does second question means? A tiny neutrally burnt electronic pressure probe is released into the inlet pipe of the water pump and transmits 2000 pressure readings per second as it passes through the pump. The same pressure probe is now fixed at one point in the flow at this Lagrangian or Eurasian measurements. Obviously, for the first measurement, since the probe moves with the flow and is neutrally bound, we are following individual fluid particles as they move through the pump. Thus, this is a Lagrangian approach. But for the second case, since the probe is instead fixed at one location in the flow, its result should be Eulerian measurements. So this is option B. Yeah, option B is correct. Now solve this. In a flow field, the velocity components are given as u is equal to ax square minus y square and v is minus 2axy and w is equal to 0. Check whether you can form a stream function for this flow field. If so, what is the stream function? Okay, I'll give you some time here to solve this and then we'll proceed with the solution. Okay. Okay, so just 1 second, let me connect the writing pad. Excuse me. Okay, so for this, first of all, let me change the color. This question number 3. So u is given as a of x square minus y square, and v is given as minus 2axy, and w is given as 0. As w is given as 0, the flow is 2D. So we need to check whether the flow is now incompressible or not. So for incompressible fluid, obviously we know del u del x plus del v del y is equal to 0. Right? Now, del u del x is equal to 2ax, and del v del y, if we will write this will be is equal to minus 2ax. So if we will form del u del x plus del v del y, that will be is equal to 0. Del u del x plus del v del y is equal to 0. That is, the fluid is incompressible. The fluid is incompressible, and the continuity equation is del u del x plus del v del y is equal to 0, is satisfied. Now we can define the scalar stream function psi as u is equal to del psi del y is equal to a x square minus y square, and psi is, if we'll integrate this is equal to u dy plus some function x. So psi is equal to, if we'll integrate u, so this will be a square ax square y minus a y cube upon 3 plus function of x. Let's suppose this is equation number 1. Now if we will differentiate it, this will be del psi del x is equal to 2axy plus f dash x. Let's suppose this is equation 2. Now if we will do v is equal to del psi del x is equal to minus 2axy. So del psi del x is equal to 2axy. If del psi del x is equal to 2xy, if we will put this in equation 2, so we will find f dash x is equal to 0, or fx is equal to c. Put this in equation 1. So if we will put this in equation 1, psi will come out to be ax square y minus ay cube by 3 plus c. This will be the equation. This is the equation of stream function. Okay, let's move to the next question. So a two-dimensional flow is described in the Lagrangian system as x is equal to x naught e to the power minus kt, and y naught plus y naught 1 minus e to the power minus 2 kt. Y is equal to y naught e to the power kt. So the equation for the fluid particle in the flow field, we have to find the equation that is the for the Lagrangian approach. So what we need to do, x and y is given, we'll just replace t and combine both of the equation to form an equation of y with respect to x. Because x naught y not known, xy is known, but we don't know t. So t we need to replace. And the velocity components in the Eulerian system. So velocity components means u. So u will be del x del y. So del u is equal to del x del t, and v is equal to del y del t. So we will just replace that and yeah, and replace this, and we'll form some like we'll find some equation of like u and v both. So that will be the velocity components of the Eulerian system. So I'll give you 2 minutes to solve this, 3-4 minutes rather, and then we'll proceed with the solution. So if we go on to the solution of this, first of all, the trajectory of fluid particle in the flow field is found by eliminating t from the equation, as I already explained before. That will be helping in describing its motion. So first of all, e to the power kt, we have to just eliminate it. So in the y equation, this we can replace, right, with y upon y naught. So in the x equation, x equal to x naught, y naught upon y plus y naught 1 minus y naught square upon y square. So if we will solve this, this will be x minus x naught, y square minus x naught y naught y plus y naught q is equal to 0. So this is the equation for the fluid particle in the flow field for Lagrangian approach. Next, for the part B, as I said, u will be the x component of velocity, that is dx upon dt for Eulerian approach. So this is d dt of x naught e to the power minus kt plus y naught 1 minus e to the power minus 2 kt. Right. So this will be is equal to minus k x naught e to the power minus kt plus 2k y naught e to the power minus 2 kt is equal to minus k x minus y naught 1 minus e to the power minus 2 kt plus 2 k y naught e to the power minus 2 kt is equal to minus k x plus k y e to the power minus 2 kt plus e to the power minus 3 kt. So it's like v, that is the y component of velocity, is equal to dy dt is equal to d dt of y naught e to the power kt. This will be is equal to k e to the power kt y naught. So this y naught e to the power kt is equal to y. So this will be ky. Okay, so let's proceed to the next question now. A velocity field is given and we need to find the acceleration of the fluid particle at 2, 4, minus 4 and at time t. So this is very easy. So we already know the formula for the substantial derivative of acceleration. So we'll use that to find this out. Okay, I'll give you 2 minutes to solve this. So let us go and solve this. So it's like here acceleration is given, like acceleration we know that it will be substantial derivative of v, right? So that is del v del t plus v del v. So del v del t is equal to 2I plus 4x t k. So v del v is equal to u del x plus v del y plus w del z. So this is equal to 4 plus xy plus 2ti plus 6x cube j plus 2xt square plus z. Okay. So this is equal to u yi plus 18x square j plus 3t square k plus v xi plus wk. So this is equal to, this is the convective part basically. So 4 plus xy plus 2t yi plus 18x square j plus 3t square k. So this is equal to, sorry, t square k plus 6x cube xi plus 2xt square plus zk. So that is equal to 4y plus xy square plus 2t y plus 6x to the power 4, this is I, yeah, plus 72x square plus 18x cube y plus 36tx square j plus 12t square plus 3xyt square plus 6t cube plus 3xt square plus zk. Now, finally, the acceleration field can be expressed as 2 plus 4y plus xy square plus 2ty plus 6x to the power 4I plus 72x square plus 18x cube y plus 36tx square I, sorry, j plus 6xt plus 12t square plus 3xyt square plus 6t cube plus 3xt square plus z. Okay. The acceleration vector at the point 2, 4 and minus 4 and time t is equal to t can be found by substituting the values of x, y, z and t. So if you will substitute this, you will find, so, oh sorry, there is one slight problem. So this is 4 x to the power 4. Just one second. This is 4xt, right? So 4xt. This is 4xt. So this will come as, just one second. Let me see. So this is question of 1. Came about 278. So this is, so A vector will come about 170 whole square plus 1296 plus 248 whole square half. That means 170 I cap plus 1296 j cap plus 572 k cap. So that means 13. Let me check here. 1336 270 1336 1336 units is 278. Okay, so this is the final answer. Let's proceed to the next question. So we need to find the acceleration at point 111 for the flow following flow field. U is given, P is given, and W is given. So okay, I'll give you some time to solve this, and let's proceed with the solution after that. Okay, so let's proceed with the solution. Let me connect with this first. So this is question number 6. So the x component, so the x component of acceleration ax is equal to del u del t
plus u del x plus v del y plus w del z. So this is equal to 0 plus 2x square plus 3y 4x plus minus 2xy plus 3y square plus 3z by 3 plus 0. So if we'll put all the values x, y and z 1, 1, 1 and t also 1. So if you put the values, this will be 0 plus 5 into 4 plus 4 into 3 plus 0. This will be equal to 32 units. This is AX 1, 1 and 1. Similarly, y component of acceleration. AY is equal to del V del T plus U del V del X plus V del V del Y plus W del V del Z. So this is equal to 0 plus 2x squared plus 3y minus 2y. We are just differentiating with nothing else. So plus minus 2xy plus 3y squared plus 3y plus minus 2x plus 6y plus 3z. Now plus 3 by 2 z square plus 2xz. Sorry, here it will be minus 9y square z 3y. So ay 1 1 1 is equal to 5 into minus 2 plus 4 into 7 plus minus 8.5 into 3 is equal to minus 7.5 units. Again, z component of acceleration. So az is equal to del w del t plus u del w del x plus v del w del y plus w del w del t z. Sorry. So this will be is equal to 0 plus 2x square plus 3y into 2z plus minus 2xy plus 3y square plus 3zy minus 18xyz plus minus 3 by 2z square plus 2xz minus 9y square z minus 3z plus 2x minus 9y square. So that az at 1, 1, 1 is equal to 0 plus 2 plus 3 into 2 minus minus 2 plus 3 plus 3 18 plus minus 3 by 2 plus 2 minus 9 minus 3 plus 2 minus 9 is equal to 23 units. Okay, this is it. Now let's proceed to the next question. Mm,
So the velocity and the density fields in a diffuser are given as U is equal to U naught e to the power minus 2x by L, and rho is equal to rho naught e to the power minus x by L. Find the rate of change of density at x is equal to L. Okay. So we need to find the rate of change of density. So it's very easy. It will take only 1 minute to solve this. So I'll give you 1 minute to solve this and then we'll proceed with the solution. Okay, so let's solve this then. This is nothing but first we need to find the like the rate of change of density. The rate of change of density, but density may change with xyz also. That means there may be like change of density with position as well. So we need to consider both position and temporal variation. So we need to consider the substantial derivative in all. So d rho del dt is equal to del rho del t plus u del rho del x. So del rho del t, there is no variation with t. So this will be 0 plus u naught e to the power 2x upon f. This is u, and the del is varying only with x. So rho naught e to the power minus x by l. So this will be is equal to u naught e to the power minus 2x by l and minus rho naught by l e to the power minus x by l. So this is equal to minus rho naught u naught by l e to the power minus 3x by l. So at x is equal to l, d rho by dt is equal to minus rho naught u naught by l e to the power minus 3. So this is the change of rate of change of density. Okay. So next question in the similar pattern. A fluid is flowing at a constant volume volumetric flow rate of Q through a divergent pipe. Here we can see that the diameter of the pipe is increasing, having an inlet and outlet dia of D1 and D2 respectively, and a length of m. Assuming the velocity to be axial and uniform at any section, find the acceleration at the inlet and outlet of the pipe. Okay. So we need to find the acceleration. So for this, we can take like if we consider the similarity of this figure. So if we consider that similarity only, so dx is some dia in between d1 and d2. So dx can be written as d1 plus x by l d2 minus d1. So the uh, uh, this we can use actually. So just 1 second, sorry. So volumetric flow rate if is q, we can write volumetric flow rate equal to area into velocity. So area will be pi d square by 4 into velocity. So velocity is equal to 4q upon pi. D is d1 plus x by l d2 minus d1 whole square. So you can easily solve this, and from this you know now. So from that you can find the acceleration. So I'll give you 2 minutes to solve this. Okay. So if we will solve this, so acceleration at that section can be written as u del u del x. Sorry. Because uh, the velocity is to be calculated at the axial distance, like at axis. So at axis we'll be considering that the other acceleration in other direction is negligible. So this is 4q pi d1 plus x by l d2 minus d1 whole square multiplied by minus 8q pi d1 plus x by l d2 minus d1 whole cube d2 minus d1 upon l. So this is equal to minus 32q square, sorry, d2 minus d1 upon pi square l d1 plus x by l d2 minus d1 whole to the power 5. This is the general expression for acceleration at any section at any distance x from the inlet of the pipe. So substituting the value of x equal to 0 and x equal to L at inlet and outlet respectively, if we will do that, then acceleration at inlet will be minus 32q square d2 minus d1 upon pi square L d1 to the power 5, and acceleration at outlet will be minus 32q square d2 minus d1 upon pi square L d2 to the power 5. Okay, so this is it for this question. So let's proceed to the next question now. So this seems very tough, but this is not. This simple, rather easy problem. So it said that for a hypothetical flow, the velocity field from time t is equal to 0 to time t is equal to 10 second was u is equal to 0, v is equal to minus 3. That is from t to 0 to 10, we will consider u0, v minus 3 meter per second, and w is equal to 0. And from time t 10 to 20 seconds, the velocity will be considered as u is equal to 2 meter per second, v is equal to 0, w is equal to 0. So there are four things that we need to find out. First, the equation of streamline. Second, the first equation of streamline at t is equal to 6 seconds. That will be considered in between 0 to 10 seconds. So we'll use the u, v and w accordingly. Second is for t is equal to 80 seconds. That is in between t 10 to 20 seconds. And third is we need to find the location of the particle at t is equal to 5 seconds. So which was located at point 10, 10, 10, 10 at t is equal to 0. So this is just we'll find the like from u v we'll find x equation, y equation, and then replace t, and like we'll just find x equation, y equation, and when we'll find x y equation in terms of some value or some point x I y I, then we'll just find that final position xf and yf in terms of the point. Let's suppose the xi yi, that point we have considered is this point that is already given in the question, that is 10 10, and at t is equal to 0. So from that we'll find x and y. So just nothing, simple, like this is just Lagrangian approach, right? So what we will do, u, v, w we know. From that we'll just find the corresponding x and y. So that corresponding x, y, we'll just put other values, the values that the point values that are already given. So we'll put that values and find the corresponding position at that value, at that point, right? So Similarly, the next question, that is question number D, can be done. So yeah, I'll give you 4 minutes to solve this, and then we'll proceed with the solution.
Okay. So let me share my writing pad. So this is question number 9. So first, for the first part, at t is equal to 6 seconds, we need to find out velocity of in x direction is 0, in y direction is minus 3 meter per second. So the equation of streamline is given by v dx minus u dy is equal to 0, or minus 3 dx is equal to 0, or x is equal to constant. Okay, that means it is option D, right? For the part B, at t is equal to 18 seconds, that means u is equal to 2 meter per second and b is equal to 0. This means the equation of streamline will be v dx minus u dy is equal to 0, or minus 2 dy is equal to 0, or y is equal to constant. That means option C. For the third part, let us consider a fluid particle that is located at point xi and yi. Okay, so at time t is equal to ti. That means t is in between 0 to 10 seconds. Let xf and yf be the coordinates of this fluid particle that we need to find out. X final and y final, that are the coordinates of the fluid particle. So for t less than 10 seconds, u is equal to 0 and v is equal to minus 3 meter per second. Okay, so dy dt is equal to v is equal to minus 3 meter per second. So yi to yf dy is equal to ti to tf minus 3 dt. So yf minus yi is equal to minus 3 tf minus ti. So yf is equal to yi minus 3 tf minus ti. So this is one equation. Another equation is dx by dt is equal to u is equal to 0, or xf is equal to xi. Now xi and yi is equal to 10 is 10 10. Both are 10 and ti is equal to 0. It's already given in the question, right? The location of this fluid particle at any time tf, that is between 0 and 10 seconds, can be obtained using yf is equal to, so in this equation yf is equal to 10 minus 3 tf, and xf, in this equation xf is equal to xi is equal to 10. So this we need to find that t is equal to 5 seconds. So this will come to be minus 5. So that means the value, the position is 10 minus 5. That means option B. Okay. For the
fourth question, similarly, like what we have done, we are taking same point xi, yi, and similarly we'll do for yf, we'll get the equation yf is equal to yi minus 3 10 minus ti. How? Actually, dy by dt is equal to v uh, is equal to minus 3 dt, sorry, minus 3, right? 1 second. Minus 3. Okay, so dy is equal to minus 3 dt plus 0 dt. So this is equal to yi to y final, that is yf, that is the point that we need to find out, ti to 10 and 10 to tf. We have just divided it into two parts. Of course, this actually takes the whole toll, like from if we are taking at 15 seconds, that will also consider for like that will also consider the below 10 seconds. Below 10 seconds, it will be minus 3. Okay, so we just divided, so this will be yf minus yi is equal to minus 3 10 minus ti plus 0. So this will be is equal to yf is equal to yi plus, not plus, sorry, 1 second, minus 3 10 minus ti. So this is yf equation. Another equation is dx upon dt is equal to u, and it is 0 for t less than 10 seconds and 2 for t greater than 10 seconds. So that means xi to xf dx is equal to ti to 10 0 dt plus 10 to tf to dt, or xf minus xi is equal to 0 plus 2 tf minus 10, or xf is equal to xi plus 2 tf minus 10. So given xi and yi is equal to 10 at ti is equal to 0. So using these values, we'll just put the value here and in this equation and in this equation. So we'll get yf is equal to yi minus 3 10 minus ti, that is minus 20, and xf is equal to 10 plus 2 tf minus 10. So this will come to be 20. So the point is 20 minus 20. Okay. With this, let's proceed to the next question. We are left with 3 more questions. So this is very easy question rather. An infinitesimally small fluid element is subject to the velocity field u is equal to k x plus y, and v is equal to kx minus y, and w is equal to 0. So determine the acceleration of the fluid element along x direction. Which among the fluid statement is true for if k less than 0? And that is about the elongation and contraction. We need to check this. Determine the rate of volumetric strain on the fluid element. Okay, so I'll give you 2 minutes to solve this, then we'll proceed with the solution.
Okay, so first of all, the acceleration will be del u del t plus q del u del x plus v del u del y plus w del u del z. So that will be is equal to 0 plus k square x plus y plus k square x minus y plus 0. This will be is equal to 2k square x. That means option B. Next, for part B, this will be u is equal to, it's given as k x plus y and v is equal to k x minus y. So the linear strain rate along x is equal to del u del x is equal to k, not minus k, k. So and along y is equal to del v del y is equal to minus k. So this means that if k less than 0, then there is elongation of the fluid element y. Like k if less than 0, then this is decreasing and this is increasing. That means there will be elongation of the fluid element along y axis. Like if this is the fluid element, if I'll use some other color, there will be elongation x direction and there will be contraction in y direction. Like this will be the new, like, so sorry, elongation in the y direction and contraction in x direction. Like this will be the new fluid element, right? So part C, this will be the rate of volumetric strain, that is del u del x plus del v del y, that is k minus k is equal to 0. Okay, so we have two more questions left. Let's proceed faster. So it said that the velocity components in an unsteady plane flow are given as u and v like this. Determine the equation for path line subjected to x is equal to x naught and t is equal to t naught. Very easy, like already we have done this kind of problem, so it's very easy, like question number 11, right? So u is given as x 1 plus t, x upon 1 plus t, and v is given as 2y upon 2 plus t. So dx upon dt is equal to x upon 1 plus t and dy upon dt is equal to 2y upon 2 plus t. So if we integrate this, ln x is equal to ln 1 plus t and ln y is equal to 2 ln 2 plus t plus c2 dash plus c1 dash. So let's suppose c1 is equal to ln c1 dash and c2 is equal to ln c2 dash. Then we can write this as like x naught, sorry, x is equal to x is equal to 1 plus t into c1 and y is equal to 2 plus t whole square c2, where now initial condition is given that t is equal to t naught. When t is equal to t naught, x is equal to x naught, right? So we'll just put this in the main equation. So x naught is equal to 1 plus t naught c1. So c1 is equal to x naught upon 1 upon upon 1 plus t naught. So x is equal to x naught 1 plus t and 1 plus t naught. And similarly, y we can find out as y naught 2 plus t whole square and 2 plus t naught whole square. So now similarly we need to just eliminate t. So from this we can write
we can take t is equal to, from this we can take t is equal to x upon x naught 1 plus t naught minus 1. So in this equation, in equation of y, we can write y upon y naught 2 plus t naught whole square is equal to 1 plus x 1 plus t naught upon x naught whole square. This is the main equation, that is option A is correct. Now this is the last. Nadir is washing her car using a nozzle similar to the one that is shown here. The nozzle is 0.325 feet long with an inlet diameter of 0.035 feet and outlet diameter of 0.182 inch. The volumetric flow rate is given as 0.00187 feet cubic feet per second, and the flow is steady. Estimate the magnitude of acceleration. So moving down the central line. So as it is considered central line, again we will consider acceleration only along x direction. Other accelerations won't be considered, like and also the acceleration is considered along x direction, and along with this we won't be considering any velocity towards y direction or z direction, right? And also the x component velocity won't vary with y and z. So having said that, let's solve this. Del v del t is equal to 0. Obviously there is no local acceleration, there will only be advective acceleration. So v vector dot del whole v, this won't be is equal to 0. First let us find the inlet velocity is equal to the volumetric flow rate upon area of inlet is equal to 4 v pi d inlet square. So this will be is equal to 4 into 0.00187 feet cube per second upon pi 0.0350 feet whole square. So this will come out to be 1.95 feet per second. And for outlet is equal to V A outlet is equal to 4 V pi D outlet square. So this is equal to, again D outlet is equal to 0.01517 feet. So this will come out to be 10.4 feet per second. Therefore, if we find out the acceleration along x direction, del u del t is equal to u del u, sorry, plus u del x plus v del u del y plus w del u del z. So obviously w is equal to 0, there is no so this u change in x and y we can consider, but the problem is here v and w will be 0, that is there will be no velocity in y and z direction. We are not considering, as it is considered in the central line. So and this is also 0. So this is u average in the whole inlet and outlet cross section del u upon del x. So by first order finite derivative approximation, this average del u del x del u and upon del x through the center line of the nozzle, we can write this as u outlet minus u inlet, and this as the whole distance of the nozzle, that is given as 0.325 feet. And u average is given as u outlet plus u inlet whole square upon 2. Sorry, not square. only there is the average velocity. So if we'll put all the values, this will come out 160 feet per second square acceleration. This is the final acceleration, right? Because there will be no acceleration in y or z direction. So, okay, sorry. So, 1 second. So that's it for today. I'll close the class here only, and I hope you have understood everything. If you are having any doubt, you can just come up in the next class. That will be at the same time at 7 p.m. to 9 p.m. on Fridays. So I'll meet you all with session 6. So that will be in the next week. And if you will be having any doubt, you can come up with that doubt in the next week. Okay. Thank you. Bye.